All right. We will now look at how to measure these radiations. Is it possible to measure these radiations, to construct a device which can detect and measure these radiations? Well, just like any other measurement that we do, radiations can be measured by the effect they produce. Now, what is the effect that they produce on the medium through which they pass through? One such effect is that they produce ionization. Now, normally, air around us is not a conductor because air doesn't contain free electric charges. But if you can have radiations all around you, if radiation is passed through air, those radiations can create ions. And when ions are generated in air, there are free charges. That means air can be made electrically conducting. You see? So this is one way to detect the presence of radiations. So radiations can be measured, detected, or measured using the effects they produce. Most radiations knock off electrons from atoms in a material producing ions. Now, an ionization counter is a device that can detect and measure ions produced by radiation. So obviously, a radiation detecting device makes use of the ionizing properties of radiation. Radiations also produce flashes or sparks when they fall on phosphorus materials, or fluorescence or phosphorescence. Some radiations, when they fall on certain materials, will result in the emission of light. That is phosphorescence or fluorescence. That property can also be used to detect these radiations. So there are two main properties that we use in detecting and measuring radiations. One is the ionizing ability of these radiations. The second is the fluorescent properties of these materials. Now, most commonly used radiation measuring device uses the property of ionization, and most commonly used measuring device for radiation is the Geiger counter. Now, I have a Geiger counter in here. This is a Geiger counter. Let me see if I can put it in a place where light will show on it. A Geiger counter. Now, what is it made of? Well, that is just a picture. That's not very useful. But I have a diagram that shows what a Geiger counter is. Now, a Geiger counter is a tube that contains a certain gas. Now, the tube is metallic, and inside the tube you have a stretched wire. And actually, the tube and these wires are two electrodes. Now, if you watch in here, this is the metal tube. I think not enough light is falling at it. And if you notice here, the wire in here is connected to the inside wire. So the outer metal cylinder is one electrode, and the inner wire is another electrode. That means if you now connect these to a battery or a power supply, if the air or the gas inside is an insulator, then no current will flow, because the current cannot flow from the outside container to the inside wire through the insulating material. But when you allow radiations to pass through here, those radiations will generate ions. And when these ions are generated, this space will become electrically conducting, and a current will flow quickly from that wire to the outer electrode. And that current or that pulse can be detected. And that is the principle of the Geiger counter. So here I have the metal cylinder here, and the wire actually does a couple of things. It provides the potential difference between the outer container and the inner wire. That is one wire that goes inside. Also, this part of it is connected to a scalar which will count the number of ionizations that happens. When a radiation goes through, there's a window in here, you can see it here. When a radiation is allowed to enter this window, if it generates an ion, it will be immediately detected and the scalar will count it. Now, here is the scalar that will count that. Let me see if I can show that to you. There is the scalar. It actually has the number in it, and that's the number of radiations that has been detected since I started this lecture. In this room, 218 radiations have been detected. That means there are stray radiations all around us, isn't it? And this is a Geiger counter. This is the counter, and this is the scalar which actually detects and counts and gives you a measure of the radiations. All right? Now, let me see. This is measuring the background radiation. Now what I'm going to do is, I'm going to use a material that is going to enhance radiations. Now this is actually the filament of a lamp. Are you familiar with gas lamps which uses this kind of filaments? Now see what happens when I keep it, well, it's not responding, I think. I have applied a very high voltage. I can actually use the scalar to generate that very high voltage. And you can see it has been counting. And let's see if I can increase the rate by bringing that material. Now you can see the number of counts is increasing tremendously. It is counting the number of radiations. Now, another material that will generate that kind of radiations is actually the porcelain. See the plates that we use for eating? I have a little porcelain material here, and I'm going to keep that. You can see that also generates large amounts of radiations. So a lot of background radiations are around which are generated by a lot of common materials that we use. Well, are these harmful? Well, our body is made to withstand a certain amount of radiations. But when the amount of radiations that our tissues are subjected exceeds that safety limit, that could be dangerous. In fact, radiations can create mutations in your cells, because what these radiations do, they will go and create ionizations, and if they hit the nucleus and create changes in the chromosomes, changes or mutations can happen, and that will create in later generations being born without limbs. And if you remember the story of what happened in Chernobyl, a nuclear accident in Russia, children are still born with limbs missing and all kinds of defects because of the mutations that these radiations the people have been subjected to in that area. And those mutations can be passed on from generation to generation. So radiation damage that is done to human beings is actually something that will pass on from generation to generation. And that is one of the things that you must be very clear about and form very, very educated opinions about the presence of radiations, and should we really need materials that generate these kind of radiations around us. Another device that is used for measuring radiations is a handheld, again a Geiger counter. If you look here, there is a Geiger counter built inside. It actually works on battery. The high voltage that is needed between that inner electrode and the outer container can be provided by that battery. And you can see it not only counts, it also produces a sound. It is useful to have an instrument like this which detects the radiation. In fact, some people say a granite counter will produce radiations because of the presence of radon there. So when we had a granite counter put on, my wife asked me about it, and I took this, and there was no effect at all. There's no radiation, there's no extra radiation generated by granite. So to wrap it up, how does a Geiger counter works? When radiation passes through the window, it ionizes some of the gas atoms, producing free electrons, and the presence of these free electrons will make the medium, the gas in between, conducting, and a pulse of electricity pass, and that can be detected, and we can measure the radiations. Well, if radiation can be measured, what is the unit for measuring radiation? Well, one unit for measuring radiations is the number of radiations per second. The number of decays per second, or activity per second, is the most common unit, and that unit is called a becquerel. Of course, a becquerel is the person who discovered radioactivity. 1 decay per second equals 1 becquerel. And older unit is the Curie, of course, after Marie Curie, named after Pierre and Marie Curie. And what's the relation between a becquerel and a Curie? 1 Curie is approximately the activity of 1 gram of radium, and it is equal to 3.7 times 10 to the power of 10 becquerel. If I have 1 gram of radium in here, these devices will go mad, because there will be how many radiations per second? There will be 3.7 times 10 to the power of 10, 37 billion radiations per second. And that is 1 Curie. So 1 Curie is the same as 3.7 times 10 to the power of 10 becquerel. Now the amount of radiation received by human, that is the biological unit of radiation, is in terms of the radiological dose. And radiation dose, that is the biological unit, is called a rem. The natural radiation that people receive a day is about 1 millirem. As I demonstrated, we actually live in a sea of radiations. Our background is filled with radiations. All kinds of sources will produce radiations, and most of it is not very harmful. We get ourselves subjected to 1 millirem of radiations a day. The SI unit for the radiation dose is actually sievert, uppercase S, lowercase v, and 1 rem is 0.01 of a sievert.